Hi everyone, I'm Andy from Adaptronic. This video is the second talk that I did at PRI in 2016. It's specifically about closed loop control, in particular PID controllers. I did this talk because a lot of tuners seem to ask the same questions about PID, and I see the same questions on Facebook groups all the time as well. So I thought this might be a useful resource for people. Now, it is quite theoretical, but I tried to keep it interactive and fun. So hopefully you'll be able to use it to get a good understanding of PID without needing to understand calculus or Laplace transforms. Thank you very much to Bradley Smith from Turning Point Technology in Queensland, who helped me out with the videoing. Thanks very much to all who attended, and I hope it's used to you. Right, hello everyone. My name's Andy from Adaptronic. We make aftermarket ECUs. And I'm here to talk about closed loop control, specifically PID. And the reason for that is that a lot of tuners ask us about this. How do you set it up? What does it mean? What does PID stand for? And I've also seen this on a lot of tuner groups on Facebook. People say, what's a good reference for it? So hopefully this will be useful. Just to let you know, this is actually the first time I've done any seminars at PRI, so I'm not a professional speaker, I'm an engineer. So for me, the glass isn't half empty or half full, it's twice as big as it needs to be. I'm also not a tuner, so I'm not here to tell you how to do your jobs or anything like that, but I do have a fairly good theoretical background, which I think can be useful for this sort of thing. Also, like I said, not a professional speaker, so I'm not going to be telling you to get up and high-five your neighbour and all that sort of thing. But I do have these Tim Tams from Australia as an audience participation incentive. So I'm going to be asking you to call out some things, and whoever calls out an answer will get Tim Tams thrown at them until we run out, and then you'll just have to participate for the joy of participation. Okay, so this is actually the second talk I'm doing here, this show. Yesterday I did one on fuel modelling. So now I'm going to do closed loop control, definitions, PID, what do they stand for, that sort of thing. And I'm also going to talk about integrator windup, because that seems to be one of the biggest problems that people have with setting up closed loop control. And then I'm going to do another talk after this one about our new ECUs and walk through the software and that sort of thing. Okay, so we'll start off with some definitions. So the measured variable is the thing that we're actually trying to control. So in the case of idle speed, for example, that would be the RPM. The set point is the engineering term for what we're trying to achieve, or a target is often what it's called in a lot of tuning software. The error is the measured value minus the target. So using the idle speed example, again, if our target's 1,000 and we're idling at 900, then our error is minus 100. Effort is the amount that we are controlling the actuator, which is going to control the machine, which has the variable that we're trying to measure. So in idle speed, it would be, say, the duty cycle on the idle control valve, or the number of steps on the motor. And closed loop and open loop, I'll just show you this. So a closed loop system is where we have a target, and we have the RPM at the right-hand side, which is what we're trying to measure. The RPM minus the target is our error. So again, positive means that we're above the target, negative means we're below. That goes into some wizard magic stuff that we don't quite understand yet, but we will in about half an hour. And then that controls the actuator on the engine, so the idle control valve or boost control valve or electronic throttle or whatever the thing is that we're trying to control. So that's called closed loop because you can see there's a big loop there. That's called the control loop. The alternative to that is open loop, which I think is a pretty silly name because there's no actual loop there. But that's what it's called, so there you go. I don't make the rules, sorry. For this to work, the controller has to have some sort of setting or table or something like that to know how hard to drive the idle valve. So whether that's a duty cycle table against coolant temperature or whatever. But the point is that it doesn't actually measure the RPM, compare that to a target, and then use that to adjust the control effort. And in reality, most systems actually use a combination of open loop and closed loop. If you try to imagine a system which only had closed loop and no open loop, if you imagine, say, if you're doing closed loop fuel control with an O2 sensor and you had no fuel map at all, it was just one cell, and you tried to drive it like that and just wait for the O2 sensor to correct the mixtures, it would be pretty awful to drive. So in reality, you need both in most circumstances. Okay, so this is Tim Tam time. I want you to think of some examples of closed loop systems. For each of them, there's going to have some function on the engine, so what you would call it as a tuner, the variable that we're measuring, and the actuator that the ECU can control, and the target. So does anyone have any ideas on function? Boost control. Hang on. I'll just tip all these out so I can get them easily. Okay, boost control. Any others? Sorry? Fuel trim, yep.
New valve lift.
Sorry?
The new valve lift.
Yep, variable valve lift, very good. Any others? Come on, there are heaps more.
Take the easy one, idle control.
Yep, idle control, yep.
Traction control.
Okay,
Cruise
so
control.
boost control?
Cruise.
Oh, cruise control, yep. Okay, I've got a really easy example that even the crappiest ECU on the market will do. Thermofan. The temperature is this set point. The actuator is the thermofan, and when it goes above the temperature, we turn it on. That controls the temperature of the engine by cooling it. And then when it goes below the temperature, we turn it off. It's not PID. It's not a a pulse width modulated thing usually, but it is actually a closed loop system. Another example, which you may not have thought of, is a rev limiter. If you're trying to get to a certain RPM, or trying to not exceed a certain RPM, you do an ignition cut or fuel cut or however you want to do it. And that brings the RPM back down. Another one, actually boost control, it's actually a closed loop system even if you don't have an ECU in there. So if you just have the compressor exit routed through to the actuator, and that pushes the wastegate flap thing and controls the boost that way. So that's still closed loop even though there's no electronics in the system. Okay, so I'm going to go through an example with some numbers here because PID is actually quite mathematical. I'm going to avoid any calculus or Laplace transforms. So if you can imagine that we've got an engine that's idling at 700 RPM with an idle duty cycle of 30%. And this engine needs 40% on the idle valve to achieve 800 RPM. If our target's 800 RPM and our current RPM is 700, then that means that our error is actually minus 100. Make sense so far? Okay, so what happens then under this wizard hat to control the idle speed? What would it need to do to get it up to the 800 RPM? Sorry? Sorry?
It's opening up the idle air control.
Oh yeah, so it has to do that. It has to do that, but how much and when and under what conditions? So you and I know, because I've just told you, that we need another 10% of idle effort, idle duty cycle, to get to our target, but it doesn't know that. So the simplest thing to do is we could take we could look at the error, which is minus 100 RPM, take a percentage of that and add that to our duty cycle. So for argument's sake, if we take 10% of that, then our 100 RPM error becomes 10%. We add that to our 30%, we end up with 40%. We're at 800 RPM now. Happy days? No, not happy days. Not happy days, because now we're at 800 RPM, so our error is 0. So now our new effort is 30% because it's our base value plus 10% of the error. So we go back down to 700 RPM with 30%. So now we're going to go back. So it's going to oscillate between 700 and 800 RPM and between 30 and 40% duty cycle. Now there's actually going to be an equilibrium point there of 35% effort and 750 RPM. That's the point where the error exactly matches the gain times the extra percentage that we need to give to the idle valve. So it'll actually be steady at that point, it won't oscillate. But there's a couple of problems here. First of all, that's 750 RPM, not 800. Right, so there's still a constant error there. It's never actually going to reach 800 and stay there. And the second problem is that there's this oscillation problem that's going to occur. If you reduce the gain, so instead of having 10% of the error, say we only have 5% of the error, then it might not oscillate, but then the steady state error is going to be even greater. It's only going to get to, what's that, 733 RPM or 725 RPM or something like that. So that's a problem. It's still better than not doing anything though. Now, I want you to think, can you think of a mechanical system that's similar to a proportional controller like that? So a thing where the amount of error that you have is proportional to how hard it tries to correct it.
Like boost duty cycle and all?
Not talking about duty cycle, I'm talking about a completely mechanical system, no electronics, no thought, just a... Sorry? Beautiful. Yep. Thermostat, yep. That'll work. The examples I had were... Sorry? But that's not closed loop though. It's not actually resisting. It doesn't have a target that it will sort of be happy at and then resist from that. The examples that I was thinking of were a fuel pressure regulator. So the way that happens is that you've got a diaphragm inside. The pressure difference acts on the diaphragm, makes a force. The force acts on the spring. And depending on how hard you push the spring, depends on how far it moves, right? And you push the spring with twice as much force, it moves twice as far. So that's the proportional thing, and you can put in a stiffer spring or a weaker spring to change that percentage. And as that happens, if you went to my talk yesterday, fuel pressure regulators always do have a steady state error. The more fuel that you flow through them, the higher the pressure becomes. Or, the higher your injected duty cycle becomes, the lower the pressure becomes, even on the best regulators in the world. Wastegate, like the example I gave before, if you've just got a mechanical wastegate. And we all know what happens if you've got an actuator spring that's a bit too weak and your wastegate's a bit too small, you end up with boost creep at high RPM. And one of the ways that you can fix that, or there's a particular turbocharger manufacturer which makes these internal wastegates, makes their turbochargers with internal wastegates, and they tend to have this boost creep problem at high RPM. You can replace them with an aftermarket actuator, which I assume has just got a stiffer spring inside, and they don't do that as much, and that's just because that the proportional gain is higher. But it's still there. There's still steady state error. And an even more obvious example, a spring itself. If you imagine a suspension spring on a car, where the happy point, if you like, or where it's exerting zero force is the uncompressed length of the spring. If you drop the car like that, it's always going to sit a bit lower. You put more weight in it and it'll force back up, proportionally. And if you hit the car, it's just going to bounce up and down. It's going to oscillate, just like the example we had before. Okay, so the question is, can we somehow remember that 10% that we needed to get to that 800 RPM? Can we add it up over time to get there so that we get rid of that steady state error and end up at 800 instead of 750 or wherever? And the answer is, yeah, we can. So for example, if we wanted to get 1% of the error and then add that every second. So in the first second, we've got 100 RPM error, and then so we'll add 1%, so we go from 30 to 31% duty cycle. Then the next second, we go to 32%, 33%, and so on. Then after 10 seconds, we'll be at 800 RPM, 40% duty cycle. Happy days, right? No, not happy days, because for a start, it's going to take longer than 10 seconds to get there. Why is it going to take longer than 10 seconds? Well, I lied. So here's our target of 800 RPM. Here's where we are at 700, right? And our idle duty cycle is here at 30. So that's not really well lined up. Okay, there we go. So 1% of that is 1%, right? So go up to 31, right? But now we're not at 700 RPM anymore. We're at 710. So now this new error is not 100 RPM anymore. It's only 90. So that means that we're only going to go up 0.9 here, so it's 31.9. So it goes up a bit more. And that's not quite 80, it's 81 or something. So it goes up a bit less. So it eventually gets closer and closer and closer. And eventually, as time approaches infinity, it'll get to 800. But it's going to take longer than 10 seconds to get there, so that's a pain. Can we just add 2% each time instead? Well, yeah, you can, but you end up with this oscillation problem. But we get rid of the steady state error. So that's a good thing. It's a good thing to remember. It's not enough, but it's something that will help. I couldn't really think of any good mechanical examples of this. Sorry. Probably the best I could think of was a toilet cistern where it remembers, if you like, the volume of water, and then when it gets to a certain point, the float valve shuts it off. But that's not a proportional thing, it's an on-off thing, but anyway. Okay, so the other problem is that we have to have some way to damp the oscillations. The reason being that if you only rely on the previous proportional and integral terms that I described before, it's going to be too slow. So you need to be able to have a large amount of proportional gain and somehow deal with the oscillations. By the way, fuel pressure regulators, if you have large fuel pulses, you can actually get them to oscillate at certain frequencies. And that's why on factory fuel rails they have dampers on them to deal with those oscillations. And these days with people removing those and putting on billet rails and using hard Teflon coated lines to deal with ethanol, fuel pressure oscillations in rails actually becomes a big problem. So how can we damp the oscillations? Well, normally the way you do this is by attempting to operate against the direction of change. So rather than looking at the RPM, we'll look at how quickly the RPM is increasing or decreasing. So if the RPM is dropping quickly, then we'd actually increase our duty cycle to try and stop it dropping. If it's increasing quickly, then we'd decrease the duty cycle to try and counteract that. And again, that's going to be proportional. So if it drops twice as quickly, we'd open it twice as much. And the mechanical analogue of this is, of course, a shock absorber or a damper. If you've got a constant length on it, it doesn't exert any force at all. And the faster you move it, the harder the force it responds with. And as you probably also know, if you've ever played with adjustable shocks, you have to match it to the spring. If you turn it all the way to the soft setting, and you've got fairly stiff springs, then the car's going to oscillate. So it's not giving enough damping. And if you turn it all the way hard, then it'll actually slow down the response of the spring, and the suspension will be too stiff. So in practice, what you need is a combination of the proportional and the integral and the differential gains, and they'll need to work together. I'll go through how you work out what those gains need to be empirically when you've actually got a system that you can play with. And we've actually got a system downstairs which I invite you all to have a look at as well. But I'll tell you about that later. Now, the next thing that I need to talk about though is a problem called integrator wind-up. Now, we have this system here where, because of the integral term, our duty cycle can increase or decrease over time continuously, while ever there's an error there. So what we have to make sure is that we're actually in control of the system that we're trying to measure at the time. Otherwise, it's going to go all the way one way or all the way the other way. I'll give you an example of that with idle speed control. I bring that up because I care about drivability. The ECU has to have some way of knowing whether it's actually in control of the idle speed or not. So for example, sometimes people say, well, can't you just look to see if the throttle's closed? Can we just look to see if the throttle's closed? No, because you might be in gear, driving along with the throttle closed, and the engine might be at, say, 2,000 RPM because you're traveling at 30 miles an hour or whatever. So the car's pushing along the engine, if you know what I mean. So if you have the ECU in closed loop idle control at that time, then it's going to say, well, we're idling too high at the moment because we're targeting 800 and we're actually at 2000, even though because it doesn't know that the engine's not actually idling. And it'll keep dropping down the duty cycle. Then you put your foot on the clutch when you stop the car and the engine stalls. So that's a particular problem. And the way that different manufacturers get around this is by having either clutch or neutral switches or a vehicle speed sensor, and then it only goes into closed loop when the car's stationary. Another example is boost control. If you're trying to target a certain amount of boost and the turbo's not actually spun up yet, so it can't actually make the boost that you're trying to target, then the boost control is going to keep increasing the duty cycle in vain because there's no way the turbo can make that boost yet. And then when at the higher RPM, when the turbo does come on boost, you're actually going to get a boost spike because of this integrated wind-up problem. And actually, I'm not sure if I can say the name of the manufacturer because it might be privileged information, but one particular aftermarket boost controller that you can buy, I was talking to one of the engineers and I asked them about this problem because I was part of a team in the Bathurst 12-hour race, and we lost a car because it started to rain and we were still on slicks, and I think the driver got a bit happy with the pedal and that sort of thing. But he was at part throttle. The owner of the car asked me to look through the logs afterwards, right, as you would if you owned the car. So he was at part throttle at a small amount of boost, and then he went to a small amount more throttle, and it went up to about 12 psi of boost in the space of about 0.7 of a second, which may have caught him by surprise. And I was thinking that maybe this was actually an integrated wind-up problem where the boost controller saw that it wasn't making the boost because he was only at part throttle. And then we got a boost spike when he put his foot down. And I spoke to one of the engineers, one of the engineers that made this boost controller, and he said, no, we actually don't have any integral term. We only do P&D specifically to get around that problem. I thought, okay, that's pretty cool. Closed loop fuel is another one. If you're trying to keep doing, lambda sensing and to do fuel trims when you're in fuel cut and it's reading heaps lean because, there's all that oxygen left over. Then obviously if you get back on the pedal and it's going to be very rich because it's trimmed all the way positive. So you have to make sure that you're in open loop at the times when you're not actually in control of the variable that you're trying to manage. So if a controller is not doing what you think it should be doing and you want to see if it's because of this problem, one thing you can do is look at the logs. So for example, if you're looking at an idle speed problem, you can look at the idle duty cycle while during, say, a drive cycle, and then you can see if when you take your foot off the pedal at 2,000 RPM and the car's moving along and the idle duty cycle is going down over time, then you know that's the problem then. The other thing is that with some systems in the logs or in the live software, when you look at it, you can actually see whether it's an open loop or closed loop at the time, and you can make sure it's doing the right thing then. Another way you can check it is by actually setting the integral term to 0 and then see if you still get the problem. And if you do, and you either can't get away from this because the controller doesn't have enough information to go into closed loop or open loop, or you don't have the ability to turn it into closed loop or open loop, you can see if you can get away without the integral term. Okay, so the way that you'd normally set it up is start with PID at 000 and try to do as much control as you can on from the proportional term. The reason being that that's the fastest to act, and it doesn't suffer from integrated wind-up issues and that sort of thing. So what some people generally say to do is crank up P as far as you can before it oscillates, then use half that value. I'm a bit more aggressive, so I normally use a bit more than half that value, and then adjust I and D iteratively to suit. So I'll adjust I to get rid of the steady state error and D to adjust the oscillations. So you can see if your software allows you to do strip lines, so like a rolling log that sort of moves across the screen, then you can see the oscillations very clearly in that sort of environment. And so you can adjust D to do that. The thing that limits the amount of derivative gain that you can apply is normally how fast the system is actually sampling the variable that you're trying to control. So at, again, to come back to idle speed, often you can't use a lot of derivative control for idle speed because the measurement of RPM only happens every compression or induction stroke. So on a 6-cylinder, it's every 120 degrees, for example. So often that will limit the amount of how high you can put that D term. So if you can't get that high enough to control the oscillations, then it means that you need to reduce the P. And again, if you get I as high as possible before it starts to oscillate, then that reduces your, well, that allows it to get to the steady state as quickly as possible. What was I going to say? Okay, so I've got a couple of examples here of actual logs from people that I've seen. Now, I wonder if I can, Sean, do you know if I can turn down the house lights?
Yep.
A little bit, just to...
I don't think you can turn them off.
Okay. Do that, okay. So this is an actual log that a customer sent in, which is variable valve timing. So this green line here is our set point. So that's the angle that we're trying to reach on the intake cam. The yellow line is what we're actually measuring. So that's what the cam's actually doing. And this cyan light blue line is the duty cycle on the idle valve. Sorry, variable valve timing valve. Okay, now it looks like I've got one Tim Tam left here. So who wants to have a guess as to what's wrong with the settings? Too high on the P?
Too low on the P.
Too low on the P. Now, should I give it to the first answer or the correct answer? I'll give it to the first answer, I think. I think I already gave you one. Okay, so who was too high on the P? Maybe it's a bit hazardous doing this in the dark. Anyway, yeah, so you can see that in this area, for example, we're still above the set point, and our duty cycle is dropping, right, over time, which means it's the integral term that's doing that. But it hasn't dropped low enough yet to be able to actually bring the cam down to where it's supposed to be, or back to where it's supposed to be. So in other words, you could say he's trying to do too much with the I, but really the answer is that the P isn't high enough to actually control it. Now this is one that I did that's actually set up pretty well. So this is idle speed control before and after a power run. You can see this is a Dynapack dyno because the RPM line is perfectly straight. Now this is the idle before, so you see it's very flat. But the idle duty cycle is moving up and down a fair bit to keep that happening. So that's obviously mostly due to the D term. And then you see it goes flat during the power run because we're not in idle control then, right? Because the throttle's open. And then on the way back down, this is where I put my foot on the clutch. And it gives a little spike there. And this point here, it's actually increasing the idle effort using the derivative term to just bring it back down to idle gently. And then after that, it's very nice and flat. This is another one with the 13B. But actually, that basically just shows the same thing anyway. Okay. Now, I don't have any more Tim Tams, I'm sorry. But does anyone want to guess as to what's wrong with this one, especially here? We see this is RPM here. You can see a bit of a wiggle in the RPM, but it eventually settles down. And then we've got another wiggle there where that's supposed to be at idle. Can anyone have any ideas as to what's wrong with this one?
Red is the duty cycle?
Sorry? Yeah, red's the duty cycle, sorry. And then the light blue one's the throttle position.
Integral too high?
Derivative's too high. Yeah, so This is an example, like I said before, of where you're sort of in the limit of how much derivative you can run. So you can see the duty cycle is going up and down very quickly. The duty cycle is going up and down very quickly, and the RPM isn't moving that much, so pretty much that has to be due to the derivative. But it's actually reducing here over time, and it's getting a bit smaller. But I think we'd agree that it's not really satisfactory. You couldn't really give that back to a customer. So in this case, we need to reduce the derivative, which probably means that we'll also need to reduce at least the proportional and maybe integral as well. So yes, that's this talk is a bit shorter than one from yesterday, but basically I just wanted to, the whole point of this was that I think people can understand PID without getting into Laplace transforms and frequency domain stuffs and pole zero plots and that sort of thing. And also, a lot of this is fairly similar in terms of mechanical systems like springs and dampers. Lastly, I'm doing one more seminar here at 3 o'clock, showing our new ECUs and the new software walkthrough for that. But I thought that with PID there might be a few questions that people had, so I guess I'll open for questions now if anyone has them. Hi.
So is a mechanical example of an integral step a spool valve in power steering, where your system's up?
Yeah, we've got the reservoir that fills up with oil, you mean?
Well, I was thinking more because, while you have a lot to turn, there's a lot of assist, but then when you get to where you want to be, the assist goes back down to zero. And that's a mechanical spool valve doing that.
I'm not too familiar with how those work. I'm sorry, so I can't really.
Yeah, that's, okay.
I thought it might be proportional, but I could be wrong.
Right, okay. Just throwing my head wrapped around the I term.
The I-term is something that it integrates over time. Another way of thinking about it is, sorry, I forgot to mention, PID is also how you control other things like electronic throttle bodies. And so down at our booth at 3305, we actually have an electronic throttle body, well, two actually set up with one of our new ECUs. And I actually wrote some software that actually goes through and cycles through the different P, I, and D gains to arrive at the best ones in terms of minimum oscillation and overshoot and all that sort of thing. And so I invite you to come down and have a look at that and see it cycle through and see it eventually become happy. I tried to get a video of that for the talk today, but it's always good to see it in person where you can see the blade moving and that sort of thing as well. Do you have any other questions now?
So when you're using, in closed loop control using PID control, so I got a real problem with oscillations on a given carbon. I think, so what about when you also throw in an unknown to start with, oxygen sensor delay time, in that closed loop? If that's wrong, then I would think that would cause the P to be bouncing almost, like if it's out of phase 50%, it should be bouncing negative when it's should be bouncing positive.
That's right, yeah.
Right, so
in that case, all you
to set the response time, can you get that out using PID controls? Put a negative sign in front of there?
No, you can't, because then it'll just run away positive one way or negative the other way. All you can do is reduce the PID gains to, you can't really use D in that situation at all. But yeah, just reduce the PI gains so it accommodates it without actually oscillating. But what you might find is that you can run different gains at different engine speeds. So at higher engine speeds, you might be able to run higher gains because there'll be less transport delay.
Okay.
Okay, cool. Well, hi.
When setting up closed loop boost control, would it be better to use a longer or a shorter ramp time for the boost to build up, like in fifth gear versus first gear? Build up the boost would be different. So would it be better to set up your PID in like simulating a fifth gear pull or really narrow?
Well.
Or would it make no difference?
Really, the question is, because the turbocharger has inertia, you need to have a time thing in there as well as an RPM thing. So the way that we do it is we have a minimum boost before it'll go into closed loop, and before that it'll just do open loop. You're looking at the duty cycle table, and then after that it'll have a time delay, and that time delay is basically that's going to translate to a longer RPM in first gear compared to fifth gear, but that should be enough time for the rotor to spin up then so that you're actually in closed loop, or you're actually able to do closed loop boost then. So you have to have enough settings to be able to handle the different conditions, if that makes sense. I'm not sure about the particular boost control you're using, I'm sorry, so.
Well, the one I have in mind that I'm using at Alpha TCU to control.
Yeah, I'm sorry, I don't know how they do it. Yeah. Okay, cool. Well, thank you very much, everyone. And yes, like I said, we're doing another talk here at 3 o'clock on the new ECUs and walk through the new software. So hope that was useful. Thank you.